All right, so finally, at long last, we're going to do chapter two, the derivative. And of course, I mentioned this several times. This is possibly the most important topic in the entire course. So, because you'll continue to use derivatives throughout your entire math career, no matter how many other classes you take, there'll be derivatives everywhere you look. So, we'll start out by introducing the concept of the derivative. We'll learn the rules, and just like in the limits chapter, we start out by learning the theory behind derivatives, and then we learn the rules that enable us to actually calculate them based on whatever problem we happen to be working on. And so we'll start with the theory and work our way up to the more practical details. And so the bottom line here is that a derivative is really nothing more than a rate of change. Okay. In fact, you'll see that it can be defined as a slope. And so this is not new to us. We already understand how that works, but the concept of the derivative makes it possible to understand how much one variable impacts on another one. In other words, we can use the derivative to figure out how much a change in x will affect y. And so we see these in all applied areas. You see this quite frequently in economics, especially microeconomics. And of course, we see it in physics and we see it in all kinds of other disciplines. So the first thing we're going to do is use some graphs to try to visualize what this is all about. So you might recall the concept of a secant. If you've got some kind of a curve, it doesn't really matter what shape it has. A secant cuts through that function in two places. Okay, so this red line is a secant line because it cuts through this function f of x rather, in two different places. Now, of course, a tangent line only touches it at one point, so let me add one here. I'll use a different color. And this green line would be a tangent line. And the slope of that tangent line actually does represent the derivative of this function at this point, A. Okay, so in other words, at point A, if we're looking for this derivative of the function at that point, then what we're actually doing is we're solving for the slope of the tangent line at that point. Now, the secant line, will use that to derive the results that we need, but ultimately what we're looking for is a tangent line. All right, so first, the secant. And by the way, the notation, there's a lot of ways we can express the same information. Let's just skip ahead to the graph so you can see what this is all about. So here you can see we have that blue curve is a function of some kind. And then through that, we draw our secant line. And it connects the 2 points. Here's x, here's f of x. Now, of course, since we don't know what the function is, we can't identify what f of x is, but you can see whatever it is, it belongs here. Now, a is at some other point, and its value is right here. So the slope of the secant line, and remember the slope simply means delta y over delta x, or you can think of it as f of x2 minus f of x1. Actually, I'm running out of space here. Let me move this up here somewhere. Whoops. Okay, hold on. Here we go. So in this particular case, we can write it as f of x minus f of a, all divided by x minus a. That's where this is coming from. So again, it's just the same as any other situation you've ever been in where you calculated the slope of a straight line. It just so happens that this is a secant line. Now, sometimes it's easier to do this in the following way, and you'll see why this might be a better approach as we go along, because this makes it easier to explain things in terms of limits. Instead of using x and a, we're going to actually do this. We're going to have a, whatever this is, and f of a. What we're doing here is adding some constant h. Okay. And this is, of course, the f of a plus h. You might wonder, why does this matter? Why does it matter what we call these terms? Well, in between these two is the value of h. So what's going to happen is we're going to steadily shrink up the value of this h. In other words, we want the 2 points to get closer and closer and closer to each other. So what we're effectively doing here is taking a limit as h gets very close to 0. And we want to see what the impact is on the slope of this line. Okay, so the reason why we're writing it like this, so that what we can actually do here is find the limit of this expression as h goes to 0, which means that these 2 points are getting very, very close to each other. So now there's a lot going on here. So what I want to point out to you here is that the function is listed in black. So the orange is our initial tangent line. And what we're trying to do here is, if you notice, see, now this is using the x's like we had before. This is using the h's. H1 means that we're here. A plus H1 is here. Okay. And then when it comes to H2, that moves us here. So if you notice, these are both secant lines. We'll call this secant line 1. And this one is secant line 2. What's happening is, though, is that if we keep shrinking up the distances between a plus h and a, you can see the limiting case is this teal line. This is actually the tangent at x equals a. And so this is really what we're interested in right here. We want to know, first of all, where is this point? And then what is the slope of this line? Because it is, after all, a tangent. And so we obtained this information by taking the limit. As you can see, now they're explicitly showing you the limit. The limit as h goes to 0, meaning that these points get closer and closer to each other, is equal to the slope of the tangent line at point A. And that, in turn, as we'll see in a bit, is the derivative of f of x at A. All right. So graphically, this is an attempt to let you visualize what exactly is happening when we solve for a derivative. What we're effectively doing, as we see here, is taking the limit. As 2 points get closer to each other, the limit of the tangent line slope, the secant rather, is the tangent line. Okay, so with all that being said, we're going to use this notation going forward, and c is a constant, and delta x is a very small change in x. Okay, so we're going to stick with this notation from now on, just to be consistent with the book. And if you notice here, the limit is in terms of delta x. So, for example, and by the way, you can see it's the same idea. Here it's a plus h. It makes no real difference what letters we use, but it's probably easier for us to think of the difference between the 2 points as delta x. Okay, it means the difference between the two. Okay, and so as that difference gets smaller and gets closer to zero, the limit of this expression is the slope of our tangent line. All right, so what they're going to have us do now is take this very scary looking definition and figure out the slope of the tangent line to the function f of x equals x squared at x equals 3. So in other words, what we're aiming for is this. So they're calling it m tan, the slope of the tangent line at that point. This is what we will be able to find by taking this limit. Okay, so how would that work? Okay, well, first of all, let me copy this back onto this spreadsheet, this new slide, so that you can see it. Make some room down here. Okay, so a couple of things to remember. First of all, oops, the function is f of x equals x squared. And the constant in this case is 3. Why is it 3? Because we're trying to find the point, the slope of the tangent at x equals 3. So this is our constant. Okay. So the first thing we're going to do is replace all the c's with 3's. So the only thing we've done in this first line is replace all the c's with 3's. Now, if you notice how it says 3 plus f of 3 plus delta x. So since f of x equals x squared, that means that f of 3 plus delta x must be 3 plus delta x squared. And that's what you're seeing right here. It also means that f of 3 is very simply 3 squared, or 9. And that's what you're seeing here. Now, here's the tricky part. 3 plus delta x squared. I'm going to go on to the next slide and remind you that in a case like this, we can use FOIL. And keep in mind, delta x is a constant. So we can multiply these out using FOIL. Here's F. Here's O. Here's I. That's also 3 delta x. And then last is these two, which we'll write as delta x squared. Now, as far as notation is concerned, you can write it like this. With the understanding that it means the entire expression delta x is a single term. When we square it, this is what we get. Now, when I add these up, okay, so we'll copy this back here. In fact, there it is right there. And then, of course, remember the 3 squared is 9. So this is where we are now. So algebraically, what is this equal to? So whenever we're taking a limit like this, what we should probably do is simplify the expression algebraically as much as possible before we actually attempt to take the limit. And these two drop out, so we end up with this. Now, algebraically, you notice how delta x is a common factor for both of these terms. So we've got the limit as delta x goes to 0 of 6 plus delta x. Remember, based on the last chapter, that means all you're doing is replacing delta x with 0, and here's our limit. 6. So that 6 is the slope of the tangent line at x equals 3. So the slope of the tangent line is 6. So that is not only the slope of the tangent line, but this also is the derivative of f of x when x equals 3. So again, remember, it's a rate of change. The slope is a rate of change. So in other words, between x and let's say I go from x equals 3 to x equals 3.0001, the change between the two is 0.0001, which means that the new value of f of x should be approximately 3 plus 6 times this change, and that's going to give me 3.0006. Okay, now that's only approximately correct, by the way, but in other words, what it's saying to us is that every 1 unit increase in x at this point will lead to a 6 unit increase in f of x. Okay, now this is only strictly true or very accurate if this change in x is extremely small. If we try to go, for example, from 3 to 4, then the accuracy would break down quite a bit. So, delta x is meant to represent a very small change in x. And if that's true, if it is a very small change in x, then we should be able to use this result to come up with a new value of f of x if x changes by some small amount. Okay, so this is what it's supposed to look like. At exactly 3, you notice how the slope is 6. Okay, so right there at that point, the derivative is 6. Now, that tells me the derivative at a single point. We can also define the derivative for the entire function, and this is going to be a formula that lets me figure out the derivative at any given point. So in other words, if I have this function, then I can figure out the derivative at any point by just plugging it in. Okay, here all I know is what the derivative is at x equals 3. I don't know what it is for 2 or for 4, but I can figure it out by taking the derivative of the entire function. Okay, now this is where it's starting to get very intense. And if you notice, this is the notation. Now, as is so often the case in math, there's many different equivalent notations for the same thing. This is one of the more common ways of expressing a derivative. It's written as f prime of x. That's supposed to be prime, and it's pronounced f prime of x. And if you notice, it looks a lot like what we were just doing, except that, well, you can see it's very similar, except that we're now writing it as x plus delta x minus f of x over delta x. And remember, that means that what you're looking at here, whatever point this is our x, this is point x plus delta x, where delta x is the difference between the two. This is f of x, and this is f of x plus delta x. And so the slope of this tangent line is this. Okay, actually, I'd like to write that a little bigger now, just to make sure you can read it. So based on that graph, you can see the slope of the tangent line at x is where delta x is the difference between these 2 points. Okay, that's why we can write it like that. Instead of x2 minus x1, it's understood that delta x means x2 minus x1. So that's why we can write the denominator very simply as delta x. And so now, though, what we need to do is take the limit as delta x gets smaller. So in other words, right now, whatever result we have is the slope only at that point. What we need to do is shrink up delta x as close as possible to zero to find the derivative. Okay. And so we're going to take the limit as delta x goes to zero. Now, again, we can do this algebraically. And this is what we were just doing. This is how we find the derivative at a single point C. Okay. But most of the time, this is what we're really interested in. I'm sure, of course, we might be interested in finding it at a single point, but often our objective is to find the derivative for the entire function. So here's an example of this. In fact, it's the same example we had earlier, where we had the derivative at a single point, meaning the slope of the tangent line. So remember, M10 we discovered was 6. But what we'd like now is a formula that would enable us to figure out the derivative or slope at any point on the function. And that's what we're about to do now. So this is true. And we'll see in a minute that when we derive this function, this formula rather, it will work here, but it will work for every other point as well, not just x equals 3. So how would this work? All right. Well, first of all, let's copy this formula and remind ourselves that f of x is x squared. And um, trying to find, well, first we're trying to find the general formula, and then we're trying to find the derivative at x equals 3. Okay. So here's f of 3 plus delta x minus f of 3 over delta x, as we went through earlier. That means that this is 3 plus delta x squared minus 3 squared over delta x. We've already done a lot of this before, and we discovered here that delta x goes to 0 when x equals 3. So what happens then if we don't need it at a specific value? Let's find out. All right, so let me grab this back. So remember, the function is f of x is x squared. Okay. Now, by the way, if you applied FOIL over here to x plus delta x squared, this is what you'll get. Now, I'm going to simplify this. So oops, what did I do? Nope, that's not correct. I'll tell you, let these two drop out. So we're left with 2x delta x plus delta x squared. So what we're actually going to do here is take the limit. I just realized I left out the word limit here. Hold on. Oh, okay, so now we can do just a little bit more algebra. Now, if you notice, there's a common factor here, so we're left with 2x plus delta x. And if you notice too, now we're taking a limit. That means we replace this delta x with 0. So in other words, what I've just done is not used a specific constant 3 like I did here. And so what this is telling me is that no matter where I am on this curve, since the derivative f prime of x is 2x, if I were to pick instead, let's say x equals -2, oh, and by the way, if you notice here, this slope is twice the value of x. It's not a coincidence. So in other words, here, the slope is going to be 2 times -2, which is -4. Okay, so in other words, the good thing about having this derivative like this is that no matter what point I am or where I am, my x, the derivative is simply double that point. Okay, so when x is 3, the slope or the derivative is 6. When x is -2, the slope or derivative is -4. And I can now figure out the derivative of any point um, along the horizontal axis by simply doubling it. Okay, so because the derivative f prime of x is 2x, the slope or derivative is always 2 times x. I don't need to do it over and over again. I've just got that one formula and it works for every point on the real number line. So again, how did I do that? By not replacing the x with a 3. Okay, I just left it as x. And so what I'm getting here is the formula for the derivative of the entire function. Now here, all right, this is what we just did. Except here they're solving it for x equals 2. Now we already know that that's going to be 4. But by replacing the x's with 2's, we end up with this expression. And we end up with 4, which is what we would have known. But by taking the derivative of the entire function, we don't have to go through this process for every point. So, like I said, that's usually what we're aiming for, the derivative of the entire function, as opposed to the derivative at a single point. Now, here's some important definitions. A function is said to be differentiable at a given point if it exists, the derivative that is, exists at that point. Okay, now that implies two things are true. First, the function must be continuous at that point. And secondly, there must be a unique tangent at that point. So in other words, This is one of the reasons why we care about continuity so much, because we know that if our function is discontinuous, then the derivative does not exist wherever those discontinuities are found. If we had something like this, at x equals 1, there's a hole. That means f prime of x is undefined or does not exist when x equals 1, because the function is discontinuous there. Now, as far as the unique tangent part goes, that's very difficult to visualize. Let me show you a quick example of this. Imagine yourself running across this function, our old friend, absolute value of x. Whenever you have a sharp point like this, the problem here is that the function, you've got a situation where the slope is going to be very different from one side to the other. So something like this would not be differentiable where x equals 0. Okay, so whenever you run into something like this, a sharp break means the tangent is not unique. Actually, a better way to explain that would be that the tangent, normally the tangent, if you're, finding the tangent at a single point, the tangent just slightly to the left of this point and just slightly to the right of that are quite similar. That's not true here. Okay. In other words, from here, from the negative territory to the positive territory, the slope quickly changes from -1 to +1. And that means that there's not going to be a derivative at that point. Okay, it's only at that exact point where it's 0. Even ever so slightly to the left, it's negative, to the right, it's positive. And so that rules out the possibility that there's a derivative there. Whereas the function like this one, the derivative on either side is slightly different, but not that much different. So here, with this dramatic change like that, then there is no derivative. Anyway, so let's use this new definition we just found. It's like a new toy that we have to play with it. Here's the function, and we want to find not the derivative at a single point, but the derivative for the entire function using this approach. Okay, so remember, f of x is square root of x. And so that means that this is equal to the square root of x plus delta x, and this is equal to delta x. And then we always divide by delta x. That never changes. And then we want to take the limit as delta x goes to 0. Now, if we put direct substitution right now, we're going to wind up with 0 over 0, which is not what we want, as we know. That's a real problem. But when we were studying limits, we saw that we can often find algebraic ways of dancing around this problem. So you might remember that word conjugate. Something like these two terms are conjugates of each other because they only differ by the sign of the second term. Okay, so that might give you a hint as to what we're going to do next. We're going to multiply this thing by a ratio of the conjugate of the numerator to itself. Okay, so let's see how that would work. Now, it looks like a catastrophic mess, and it kind of is. Don't worry, it'll work out. So this and this are conjugates of each other. Because again, the only way in which they differ is by the sign. Now, the reason why we're doing this, that means that when I multiply them out, there's going to be some cancellation. That's really what this is all about. Even though the denominator will get very messy, the numerator will be much simpler. And then when we substitute delta x equals 0, we can maybe avoid division by 0. So if you multiply these out with FOIL, you'll see this is what you end up with. In the denominator, all I did was multiply delta x by these two terms. You can see they're still here. Now, I can simplify the numerator as 1. Okay, in fact, I'll grab this and bring it ahead so you can remind yourselves. So this, of course, this numerator reduces to 1. Not 1, delta x, sorry. What am I saying? Um, Now, guess what? This turned out to be a good move then because these cancel each other out. And so we end up with 1 over radical x plus delta x plus delta x. And now when I plug in a 0 here, I end up with 1 over radical x plus radical x, or 1 over 2 radical x, which I can then rewrite if I want to as 1/2 x to the minus 1/2 power. And this is what we mean by f prime of x. And then I can use that to now calculate the derivative at a single point, knowing that I have the formula for the derivative of the entire function. Wow, this looks like a very scary, well, no, it's just our old friend, the square root of x. It's not obvious that the slope of this function at any given point is equal to this, but it is. This is what we just proved. Oh my God, wow. So now if I do need to know, let's say, let me just copy this. So f prime of x ultimately equals 1/2 x to the minus 1/2. So let's say I need to know the slope of this curve when x equals 3. Okay. So what I would do then is solve for f prime of 3. Whatever that is. And so that is my slope at that point. By the way, what happened here with this 1 over 2 radical 3? We normally don't we try to avoid having radicals in the denominator. Okay, how did I get around that little problem? Let me show you real quickly over here. I'm just going to multiply this by radical 3 over radical 3. We have radical 3 over 2 times 3. And that becomes radical 3 over 6. In case you've forgotten how to do this. Okay, just by convention, we normally try to avoid having radicals in the denominator. And so this is how you get around that problem. So anyway, now I can choose any other x I want, and I can always figure out the slope of the tangent line at that point or derivative by simply plugging x in to this derivative for the entire function. All right, here's another one, x squared minus 2x. First of all, let's see what this looks like with our old friend Symbolab. X squared minus 2x. Oh, it's a very nice parabola. I like that. Now, if we were looking for the solutions, we would have them right there. That would be easy. We have our minimum point, but that's not what we're aiming for right now. What we're looking for is the derivative of this function. So once again, we take out our definition. And let me quickly copy this so we don't lose it. So this is the definition. So f of x plus delta x means that you have x plus delta x squared minus 2 times x plus delta x in the first term. The second term is just the original function. Okay, now of course we're going to apply FOIL to this term. If you do that, you'll see it turns out to be x squared plus 2x delta x plus delta x squared. And you'll see that right here. Actually, I could have drawn that a little better. Then now, of course, here I've got to distribute this -2 across these two terms, -2x minus 2 delta x. Here's the same thing. I've got to distribute this negative across these two terms. This becomes plus. And now, of course, it's just a matter of simplifying, and then maybe we can reduce this a little bit. And then we take the limit by substituting 0 for delta x. Okay. So here's the simpler version, and we do have the ability to simplify. This reduces to delta x. Okay, so we're left with 2x delta x minus 2. Now I substitute the 0 for delta x, and this is my final result. Okay, so remember the original function was x squared minus 2x. The derivative is this. Okay, so no matter where I am on this curve, I can find the derivative or slope of the tangent at that point by plugging in that number into this derivative 2x minus 2. And oh, also, let me just make it clear here that this is f prime of x. So if, for example, I want to know the derivative when x equals 3, it would be 2 times 3 minus 2, which is 4. Right. By the way, like I mentioned this earlier, there's many different ways of expressing a lot of concepts in math, but the derivative of x, the most common one, I guess, would be the f prime of x. Sometimes it's written as y prime, and sometimes it's written as dy dx. Now, this is basically taken from this notation. This is approximately equal to delta y over delta x. The difference being that dy is the differential of y, and this similarly for x. And what separates the two is that delta y is a small change in y. And dy is an infinitesimal change in y. Okay, so that's, like I said before, remember we saw in that graph that if you want to figure out the slope, you can use a tiny change in y and x, or in x and figure out what the changes in y. So it's important that the changes be very small. So dy dx is often, now, by the way, part of the reason why this happens, all this different notation, is because many different mathematicians over the centuries developed the field of calculus. In particular, we have Sir Isaac Newton in England. You all know Isaac Newton. He's so famous for so many developments, discoveries, optics and the law of planetary motion and all this and that. Roughly the same time, um, in Germany, we have Gottfried Leibniz working on very similar problems. Now, they did not, as far as I know, they did not know each other. They certainly didn't communicate with each other. I mean, let's face it, this is the late 17th century. There's no reason why they would have ever known about each other. But it turns out that by kind of an interesting coincidence, they were both working on what we now know as calculus at roughly the same time. And they both jealously regarded themselves as the father of calculus. They refused to give the other any credit for it. And so it was just one of those things where they both sort of invented the same thing at the same time. But they both use slightly different notation in their writings. And so some of this notation comes from Leibniz and some of it comes from Newton. That's part of the reason why we keep running into this case where there's many different notations. Now, books have been written about this rivalry. I mean, if you wanted to, suppose you're really interested in the history of math, you could say, well, listen, let me see one of these cool books that have appeared in the press. This one just came out. Wow, look at that. Some of these have been bestsellers. You wouldn't think that the general public would care enough about calculus to read about this type of thing, but it happens. Yeah, you've got biographies of these guys, and most people have never heard of Leibniz. Everyone knows Newton, but there it is. I knew it. I remember having seen that. Calculus Wars, the greatest mathematical clash of all time. Now you can see this got 4 stars, by the way. This kind of book could be easily a bestseller. In fact, I'm sure they sold a lot of copies. Like I said, who would have thought that somebody could make this interesting enough that the public would buy a book like this? But there it is. Okay, so if you're really interested in math history, which is quite an interesting area, every discipline has its own unique history, and this is no exception. It just so happens that here the two people involved were very antagonistic towards each other. And Newton, of course, was very famous for being very secretive about his work. And so, let's just say that it was an interesting time in mathematical history. But anyway, we know that a derivative requires continuity to exist. So what that means then is that if we have some function which has A in its domain, now the way it's written, what it's saying is that here's A. If f of x is differentiable, then the function must be continuous at that point. So in other words, being differentiable implies continuity, at least at that point. Which is the same thing as saying that if it's discontinuous there can't be a derivative. Okay, but we kind of already knew that, but this is a more formal way of stating it. By the way, here's an interesting twist. You can differentiate a function more than once. Oh my God, yes. Why not? You can take what's called the second derivative and you can take a third derivative. The second derivative is the slope of the slope. In other words, it's measuring how quickly the slope is changing. The third derivative is the slope of the slope of the slope. And for some applications, we do need to take these higher order derivatives, which are called second derivatives and third derivatives. And the notation, at least here's the second derivative, of course, has to be modified. This becomes f double prime of x. This is y double prime. Now, this one comes about because here's what you're actually doing. That looks like a very odd notation. This differential notation, this is where we get this from. Okay. So if you're wondering why it's d squared y over dx squared, this is why, because this is what you're actually doing. And then, of course, we need more notation for the third derivative. Yeah, 3 primes, and then d3y over dx cubed. Now, we don't normally go much further than this. Even the third derivative, you don't run into it very often. It's really the first and second derivatives that are the ones we'll see all the time. There's a lot of practical uses for these. The third derivative, maybe you'll see it once in a while, but all you're really doing is reapplying the same procedure multiple times. Okay, so the second derivative just means you take the first derivative, whatever you get, you reapply the same rules to the second derivative. Okay, now, so much for theory. I did mention earlier that, like with the limits, we start with some theory, and then I show you actual rules that make it easier to find derivatives. What you did here is not that complicated, but that's because the functions themselves were simple. You don't want to have to go through all of this every time you calculate a derivative. It would take a long time. Okay, it's great that we know how to do this, but once we understand this, what we can do now is learn a series of rules that will give us the same results. Okay, and there's a lot of rules, especially once we start involving trig functions. But like I said, every calculus book has a list of those rules. And, it's not a question of memorizing them. It's really more a question of understanding them because they're all related to each other. All right. So why don't we dive into some of these rules? You'll be happy to see most of them are quite straightforward. There's a few that are a little tricky. So we have the constant rule, we have a power rule, we have rules for sums and differences, product rule, quotient rule, the so-called generalized power rule. The really tricky one, in my opinion, is the chain rule. That one takes a little getting used to because it involves composite functions. Okay, but we'll get to that in a bit. The others, pretty down to earth. All right, here we go. Now, remember, we did say that a derivative is a rate of change. So it stands to reason that the rate of change of a constant is 0. It doesn't change. Okay. So of course, when we take the derivative of a constant, we end up with 0. No matter what the constant is, the derivative is just 0. All right. No problems there. Now we have the power rule. We're going to get a lot of mileage out of this one. So imagine you have a function that looks like this. For example, 3x squared. Okay, this is just a constant. This is a constant too, for that matter. I guess the key here, the reason why you make a distinction between the two is that n has to be a real number. The k doesn't. You could take the derivative of, let's say, I times x squared or something like that, although we will not be doing that here. And so it turns out that the derivative is pretty straightforward. What you're basically doing is you're multiplying this entire expression by the n, and then you're subtracting 1 from that n. Okay, actually, let me do it like this. So that n is this exponent, and then this is simply n minus 1. So as a quick example of this, if I have 3x to the 7th power, I'm going to have 7 times 3x to the 6th power, because n is 7 and k is 3. And so nk to the n minus 1 is 7 times 3. Oh, I left out the x, sorry. X to the 7 minus 1, and that reduces very nicely. Oh, now you're going to get a lot of use out of this one. This is one of the more important ones. And you can see it's really not that difficult. It just takes a little practice. You don't really need to memorize it. Here's a good example. What if instead we have 3x to the 4th? Let me just put this up here. Then applying these rules, now of course this is our n, a k rather. Let's try that again. K x to the n. So therefore k is 3, n is 4. So that means that n is 4, k is 3. And in here you're just simply subtracting 1 from the n, and we end up with 12x to the 3rd. Now, if you notice, these are all polynomials, so the rules are quite simple when we apply them to polynomials. We'll see later on that they can get a little messier. Well, how about this one? We have a negative exponent. What happens then? All right, well, let's find out. So once again, just a quick reminder what the original function was. So we're going to have negative 3 times 6. And then when we subtract negative 1 from negative 3, we end up with negative 4. The final result is negative 18 to the negative 4 power. Now, let's do something interesting. Earlier, we claimed that when we had the function x squared plus 3, we went through the steps to prove, using the limits that is, that the derivative was 2x. Let me go find it. Here it is. No, it was just x squared. Okay. So when the function is x squared, the derivative we found with the limits is 2x. So what we're going to do now is prove it with our rules. All right, I lost my place. Hold on. Here it is. Here it is. Okay, so we showed already. So using limits, f prime of x, we showed it to be equal to 2x. Now here, we're going to use our power rule and show that we were right. So in this case, the k is equal to 1. There's an implied 1 here, and then n is 2. Okay, so that means when we use this rule, we're going to have 2, 1, x to the 2 minus 1, or 2 times x to the 1, or 2x. Wow, we did it right with the limit. Now, you saw how long it took to do this with the limits. Look how much quicker this is with the rules. So you can see why we're going to use the rules instead of always using limits. You only use the limits to learn how derivatives are related to limits. Once that's done, we can use the rules from now on. Okay. Now, you remember we were way, way back. We saw there's an enormous list here. We just covered the first two. Look at the rest of these. There's so many of them. All right, but at least number 3 is not too difficult. It's similar to the limit rule for sums and differences because all you're really doing is saying that if you have a function which is a sum of two other functions, the derivative of that function is nothing but the sum of the individual derivatives. And of course, the same thing will be true for differences. All right, so that's not too bad. That's not much of a stretch. Oh, there it is. Yes. And of course, it works for differences too. So remember, this was the case with limits. The limit of, if you remember, f of x plus g of x is the limit of f of x plus the limit of g of x. And the same thing was true for differences. All right, let's look at a quick example. Now we're going to, of course, apply the power rule for both of these. So here, k is 3, n is 2. For this one, k is 1. There's an implicit 1 here. And then n is 3. So g prime of x will be um, 2, 3, x to the 2 minus 1, 6x. For this one, h prime of x will be nk x to the n minus 1. And that's going to be n is 2. Oh, here it is. I was looking at the wrong one. N is 3. K is 1. X to the 3 minus 1. 3x squared. So the final result is that f prime of x, the sum, is 3x squared. Actually, let me write it in the same order. 6x Here we go. 6x plus 3x squared. And we didn't do anything different than in the previous examples, except that we had to do it twice. We have two terms, two functions, take and apply the power rule to both of them, and then add them up. And that's our final result. Now we're getting ready for the complex ones. Okay, so these are going to be a little bit more challenging. We've got the product rule. Okay, where is it? Let me just go back to the list for a second. Unfortunately, you may think that, like with the sums and differences, you're just taking the derivatives and adding them or subtracting them. That would be nice, but it doesn't work that way with the product or the quotient rule. Okay, so in other words, here, the rule for sums and differences, just quickly review that. Actually, I'll tell you what I'm going to do. I'll use plus and minus just to speed it up a bit. Not so with these two. The quotient rule in particular is fairly messy. And so the generalized power rule also a bit messy, the chain rule. So what I think we should do here, since we just started learning this stuff, we don't want to overwhelm ourselves right away. Why don't we stop here and save the really tricky ones for next time? Okay. I think that's a good idea. Um, Gives us a chance to recover from this lecture. And then what we can do is once we really understand what we've just done, then we can go ahead and dive into the product and the quotient rule. Okay. So, all right. So we'll do that next time. All right. See you next time.